All right. Okay, so today we're going to continue taking a look at the MNIST handwritten digit data set. Okay, so we'll look at the MNIST handwriting digit recognition. And I think we talked about this a little bit already. We said we've got this kind of, you got some digit here, right? And it's on a 28 by 28 pixels. So we have a total of 784 values. Okay, and this will go into our input. This is our input X. And we have 60,000 examples. I guess we've split them 60,000 in our training examples. And so our X matrix is going to be 60,000 by 784. And so we got, 784 nodes here. And then just, I'm going to, for our thing, I'm going to just have a simple, we will put 30 nodes in the hidden layer. And then our output layer will have 10 nodes. And so, you have all of these. So it's just a crazy mess, right? Okay. So you have all those weights there, and all those weights that go. And the way the output goes is, in this case, the goal, the training example will have we've got an output vector of 10, and because this one has a label of 5, the vector should be 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay, so this is how we are going to train it. And we will say, okay, currently, based on our current labels, maybe our guesses will be like 0.82, 0.85, 0.73, 0.62, 0.41, 0.81, 0.7, 0.2, 0.34, 3.1, and 0.5 or something, okay? And then all we do is we would just take the, so this is our current very bad guess. And we would say, no computer, this is a bad guess, okay? We just calculate the squared residual, the sum of squared residuals here. And then we say, this is what we want, okay? And eventually, the goal is, after training, probably a good guess, quote unquote good guess, would be something, let's move this. Okay, so 10 nodes, and then whatever. Okay, I can't figure out my computer. Okay, a good guess would be something like 0.001, 0.001, 0.001, 0.000, 1, 2, 3, 0, 1, 2, 3, 0.000, and then 0.999, and then 0.001, 0.00, 0.000, et cetera, et cetera, et cetera. That would be a good guess. If if that makes sense, okay? Where, you plug in the numbers and we get something where it's mostly zeros or things that are close to 0, and one value is close to 1. So that would be a good guess because the squared residual between the answer and the good guess is quite small. Yes, question? They're not probabilities. All they are is just numbers. They're just numbers. We're just... this is how we've coded the information. We've decided that when we run the neural network, we want all of these to be zeros, this one to be a 1, and the rest to be zeros. Okay? But if for whatever reason we said, you know what, we're going to code it so that all of these are zeros and this one is a 9 and the rest are zeros, then we would get values ranging from 0 and then this would be like 9 or something. But that's probably, that would not be good because currently, after we apply the sigmoid function to the last value, the sigmoid function squishes everything to the range of 0 to 1, right? So it makes sense. So you would have to have in another parameter that then multiplies that result by some kind of scaling factor or something. You can always make your model more complicated and add more parameters and give it more flexibility. But you always run the risk of overfitting things as well. All right, so anyway, this is what we're going to do. When we do this, okay, so we've got x. X is 60,000 by 784. We're going to multiply this by W1, our first weight matrix, which will be 784. And because the next layer has 30 nodes, it will be this, and therefore we will be at Z. Z layer 2 is going to be, I'm just going to write n by 30. Okay. And then what we're going to do is we're going to take Z, and we're going to add something called some biases. So this will be our first bias matrix. Maybe I shouldn't write it so far away. Okay, and so Z is n by 30. Okay, and what B is actually there's just one bias per node. Okay, so B is a vector. B1 is a vector of 30 values. Okay, because we have 30 nodes, we have one bias per node. One bias value per node. And all this does is, you have your sigmoid function. Adding a bias just shifts the function that way, or it shifts the function this way. Okay, so it just kind of shifts the things. It just adds a little bit of flexibility to the thing. So B is a vector of 30 values, but because Z is n by 30, what we have to do is we have to just replicate that vector of 30 n times. Okay, so the B matrix becomes just your n by 30. So we're just going to, is a vector of 30 values, but we must replicate it n times. So all n rows will have the same values going down the column. So this will also be n by 30, and that allows us to add these two together. And then we apply the sigmoid function to that, and this will give us our A matrix, which will then be n by 30, preserving the dimensionality. Okay. And so in the code to replicate this, what you'll see is something like B percent outer, percent repeat 1 n times or something like that. This is just outer multiplication, and it just takes the vector and it replicates it, okay? And then I think I think this will produce a 30 by n matrix, and so to get it n by 30, I just transpose it. So you might see some line like this in the code, which just takes your B vector and turns it into an n by 30 matrix. Okay, and then what do I do? Once I have A2, I would multiply this by, what's the next weight matrix called? Okay, we're going to multiply it by our next W matrix, okay? And so A is n by 30. W2 is going to be 30 by, how many nodes in the output layer? 10, right? And then so we will get our next Z matrix, Z3, and so this will be n by 10, and then we will add some biases here. Our second set of biases, we throw this into a function, and this will give us y hat, which will be n by 10. Okay, and then the second bias matrix looks very similar to the first bias matrix, except it's n by 10 rather than n by 30. Is that okay? All right, and so, and again, our goal is to minimize our loss function. And how are we going to, what is the algorithm we use to minimize our loss function? We call it gradient descent. Okay, we use gradient descent. All right, and so how many different parameters do we have? Well, a lot. But all the parameters are stored in, what are the matrices? We have 4 matrices now, okay? Well, actually, we have 2 matrices and 2 vectors. We have the W1 and W2 weight matrices, and then we've got the vector B1 and the vector B2 for our bias vectors. And so this means to do gradient descent, we're going to have to calculate, we use gradient descent, so we need 4 gradients, okay? And that will be the gradient of the loss function with respect to the first weight matrix, the gradient of the loss function with respect to the second weight matrix, the gradient of the loss function with respect to the first bias vector, and the gradient of the loss function with respect to the second bias vector, okay? And calculating the gradients with respect to W1 and W2 are pretty much the same as what we did earlier. I think we did this, was it on Monday? Okay, well, we did it in one of our classes, okay? And I leave it as a homework exercise for you guys to find the gradients with respect to the bias vectors. Okay, so that's part of your homework, is to work through that. Okay. And there's kind of a hint, not a hint, but because I've already done the work and I've implemented it in code, you can kind of not reverse engineer, but you can kind of, like, if the answer you get for the bias, gradient for the bias looks like it would be implemented like the way I implemented in the code, you probably did it right. Okay, if that makes sense, right? So I'm not writing out the math part for you. That's for you guys to work out. But I did write it in code, so the answer's kind of there. Okay, but anyway. That's what we have. So we have to figure this out. Okay. And again, I've already done it and I've implemented it in the code, and I'll just get to show you how it comes out. One other thing that we're going to do to handle all of these entries is that if I were to do matrix multiplication, okay? Now R handles matrix multiplication like a champ. It does a really good job, but 60,000 rows is still a lot of numbers to multiply, right? And so to say, you know what, we're going to do 60,000 by 784 times 784, like to multiply this. And this is, we have to go through all of this just to get y hat, right? And then once we get y hat, we have to calculate 4 gradients, and then we update, you know, kind of our 4 matrices, our 2 matrices and our 2 vectors, by taking a small step in the direction of the gradient. And then I have to do this whole thing again, right? So I take one little step, and then I've got to do the whole thing. And if I'm multiplying a vector with 60,000 rows for every single one of my little gradient steps, you know, we're going to make our computer work very, very, very hard, okay? And I mean, the computer's not going to complain, and it's not going to start a robot revolution, but it's a lot of work, and you're going to be waiting around for it. So one thing we do is we're going to do something called stochastic gradient descent, okay? And stochastic, anytime you hear the word stochastic, all that just means is there's some randomness happening in the process, okay? And so instead of doing all 60,000 rows, I'm going to just say, you know what? I'm going to take 10 random rows, and we will use these 10 random rows to find the gradient, okay? And then, and so I only do 10 by 784, and then I do this. I calculate my 4 gradients. I update my gradients. And then I go through and I just pick another 10 random rows. And I say, okay, let's use these 10 rows to figure out the gradient. So the true gradient, you know, depends on all 60,000, which is a lot. And I don't know what the landscape looks like. You can imagine this very complex landscape of hills and valleys. And using only 10 is going to give you this very like kind of low res map, right? So like in my brain, I'm thinking like this computer game where the real map is very complex, and if you wanted to render the entire map on your screen, it requires a lot of resources. But you just imagine being zoomed out, so you just only need a few polygons to kind of get the general idea. That's kind of what we're doing. We're just using 10 rows to kind of get just a general idea. Because whether, can I go? Okay. I can kind of assess whether something's a good fit or bad fit. You know, just with a few examples, right? So we're going to do stochastic gradient descent. Okay, and this says just select. In my case, I'm going to just do 10 or some other number. 10 random rows from the training data set. And then find the gradient. Using those 10 rows. Okay. Take a step, and then repeat. That's it. This is stochastic gradient descent. The stochastic part is the fact that we are doing 10 random rows. And this just makes our gradient calculation a lot easier, right? Because if I go back, I pull up my old lecture slide from, is it week 3 Monday? So we calculated Do we calculate the gradient here? Okay, so, when you calculate the gradient, we said it's going to be, A2 transpose times y minus y hat times all of this, and then if we continue on, it ends up being this, which requires that we, have to do y minus y hat, right? And so y is going to be either 60,000 rows or 10, okay? And then y hat will either also be 60,000 rows or 10. And so having only 10 makes this computation a lot faster. Yeah?
So when you say repeat again, so do we choose another 10 random rows or do we keep this?
We do another 10 random rows. We reselect, okay. Yeah. And it will be advised.
Do you select with?
Yeah, so generally what we do is we start off by shuffle all 60,000 rows, okay, and then we just put them in chunks of 10, and then we'll make 6,000 groups of 10, and then we will go through kind of each group of 10. So usually that's kind of what we'll do, right? But if you wanted to just randomly select, so that would be like a bootstrap gradient descent or something. You could do that, okay? But yeah, usually we'll just, because we generally don't like to throw away perfectly good data that we've collected. We are going to gather all 60,000 and then shuffle them up. Make 6,000 piles of 10, and then we'll say, okay, let's look at the first pile of 10. We'll process it, and then we'll say, great. And then we go to the next one, and we'll do that. Okay, conceptually, do we understand what we're doing? All right, so let's do this in code, and I think I uploaded this onto CCLE, and I'll probably have to throw away one of these things. I don't know, wait. Our code for, it says, this should say load. Our code to load or lead. And then this is just an updated version of this. Okay, but let's take a look. All right. So, I don't know if you downloaded, if you want to follow along on your computer, you can, you don't have to. Wait, let me just get this to fit on. This is killing me. All right. It's okay. All right, so what does my environment look like? Okay, so my environment's totally empty. I'll load up these functions, okay, and then we're gonna load in our data. So this reads it in. And okay, our data is loaded. All right, and we can just kind of take a look. We can look at the first entry, j equals 1. We'll pull this. So it says the label is 5, and then the digit itself is just a vector of 784. Most of them are zeros, meaning that most of the space is blank, and then we can just see kind of some of these spots have filled in, and then if we graph it, we can see, okay, that's a 5. All right, and then we can just kind of look at a few other things. We can say try j is 2, and then that looks like a 0 to us, and we can try j is 6, and the label says this is a 2, and let's just see what that looks like, and yeah, it looks like a 2. Okay, so the question is, can we train our neural network so that this thing will be recognized as the digit 2, okay? And so what we want to do is we want to go, rather than just saying the label which says 2, which is great for us, but bad for our neural network, we need to turn this into a vectorized version, okay? And so the vectorized version is I just made a simple function which just starts off with a vector going of 10 zeros, and then I'm saying change the 1 in position j plus 1 to a 1, okay? Which means if I vectorize the value 0, it will change the first one to a 1, and then everything else is 0. If I vectorize the value 1, then this will become a 1, or if I vectorize a 9, then the last digit becomes a 1. So we're just going to do this, and I'm going to just apply this function to all of our input values y. Okay. So now I can say, the dimensions of y, whoops. And so I've got 60,000 by 10, and let's just take a look at the first 10 or first 6 rows. And so we can see, that first digit, which was a 5, it appears right here under the 6th column, which makes sense. And then the next digit, which was a 0, appears here in the first column, so on and so forth, right? And we can kind of just compare this against here. Indeed, we have 5, 0, 4, and so on. All right, is this okay? So we've turned our the output results into kind of these vectorized 0 and 1 things. So we can say this is a good, so we have a way to decide if the fitted estimate is a good estimate or not. All right, so let's just, I don't know why we're doing that. Okay. Okay, we're going to add the sigmoid function, and then I've got the sigmoid prime function, and this will just kind of help us with the calculations of gradients. My cost function is just going to be the sum of y minus y hat. So again, we're just going to take each value minus what it is. We're going to square that difference and add them all up. Okay, and so if we get a vector of gibberish, then it will be a bad fit. And where if we get a vector where most of the values are zeros, with the exception of this one being close to like 0.999, then that's going to be a very good fit with a very small cost. So we implement our cost function right there. Is this okay? I'm using pretty much the same neural network code that we had written for least squares regression. So I'm going to say our input layer size is going to be 784. Our output layer has 10 nodes, and our hidden layer has 30 nodes. I'm going to create our first weight matrix, which is just going to be a whole bunch of random values. And I decided to go, so input layer times hidden layer, so that's going to be 784 by 30. That's how many values I need in my first weight matrix. And then I decided to do RUnif minus 0.5, so the random values go anywhere from -1/2 to +1/2. It didn't have to be that way, but I just decided to do that to kind of give it perhaps a nicer starting point. Okay. Number of rows, number of columns. So here we just get these big weight matrices of just kind of pure gibberish, right? So if I just ask for the head of W_1, it's just a whole bunch of values, right? And the dimensions of W1 are 784 by 30. The dimensions of W2 are 30 by 10. Okay. The biases, I'm going to make just some random bias values, okay? And we can ask for the dimensions of B1. It's going to be 30 by 1. And the dimensions of B2, what would the dimensions of B2 be? 10 by 1, right? Because we've got 10 nodes in our output layer. So we have this. Okay, and so stochastic batch gradient descent means that we're going to do this. So all I do is, I'm just doing some random sampling. I'm going to say n is the dimensions of y, so n is 60,000. We're going to do a batch size of 10, and then j is I'm going to just shuffle the rows 1 through 60,000. So I can ask what's the head of j, and so these are kind of the values from row 1 to row 60,000 are just all shuffled up, and these are the first 6 values. And then I'm creating a subset called j underscore sub, and this is going to help me pick the first 10 rows. And so basically j sub looks like this, and it just says kind of the first batch will be rows 1 through 10, and then the next batch will be rows 11 through 20. So I'm going to just say go from this, the first one to 1 minus the next one. Okay. So I'm going to say for I in j underscore sub, so the length of j sub is 6,000. So we're going to just run through this 6,000 times. And the rows that we're going to use, so let me just so I will just start off with 1 here. And so, so if I run this line of code, this will just subset this vector j, which is kind of the random rows, which says, go from I to basically 10. And so we can see the rows that we're going to use. These are the first 10 rows that we use. This is the first group of 10 that we'll use. Okay? And then we're going to say subset x. Those will be the training rows that we use. And we're going to divide by 255 to just scale them from 0 to 1 because our data goes from 0 to 255. And then take those rows for y and vectorize them. Okay? And we'll, or they're already vectorized in this y matrix, okay? And those will be the column y. And then all we do is we do forward feed, x times w1 gives us z2. z2 plus the biases inside the sigmoid function gives us a2. a2 times the next weight matrix gives us z3. Then we do z3 plus the biases, throw that inside the sigmoid function, and that gives us y hat. So that's just the forward feed part to give us our guesses. I've already done the math for calculating the gradients. Okay, and so I've calculated the gradients, and so the gradients are going to be, I calculate the gradient with respect to B2, the gradient with respect to W2, the gradient with respect to B1, and the gradient with respect to W1. I calculate all of those gradients based on kind of our current position. And with that, I use those values to update our weight matrices and biases. So I say, take our current weight matrix values, subtract off, take a small step in the direction opposite of the gradient. Take our current bias values, take a small step in the opposite direction of the gradient. Okay, and I just do this for all of these things. And that is gradient descent. And I say, okay, once you finish that, go back to the top and then use the next batch, right? So I is now going to be 11 because we're going to the next value in j sub. And it says use the next batch of 10 inside of 10 rows and use that to update the gradients and take a step downhill. Does that make sense? And this is it, okay? So there's no fancy, this is like our homegrown, hand-coded neural network training algorithm here, okay? Like I'm not using any kind of prepackaged functions. I'm just taking everything we've learned of matrix multiplication and adding and just throwing it into a loop, okay? So, so we'll just go ahead and do this. So I've got this, 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 and this, and then we'll just run through all 60,000 rows. We'll just let it run and it's done, okay? And so here, so we could run through it again. Right now I just said we're gonna just go through all 60,000 test cases 10 at a time, and I just did it once. And I stopped. I could say, you know what, I want to shuffle this up again and go through the entire deck of 60,000 and continue training, but just so you guys can see if this worked or not, we'll just stop here, okay? We can always keep running the thing if we wanted to, but we're just gonna stop. So just looking at 60,000 things. So now what we wanna do is we wanna be able to go back from our, so if we have a vector of, you know, a bunch of zeros and ones, we want to convert it back to a label. Okay, and now all this does is it just says multiply this by 0 through 9 and add that, take that sum, and it's hoping everything adds up to 0. Okay, so let's, here, before I go into this entire thing, I'm going to just kind of skip ahead, and let's just kind of see how it worked, right? So I'll say take j equals to 2, okay? So if we look at this, this has a label of 0, and if we, the digit looks like this, okay? And what gradient descent succeeded in doing is that it gave us our weight and our bias matrices, okay? So now if we feed this through, we're hoping that when we feed this through, it will give us a good guess. We're hoping this will give us a good guess of what this digit should be, okay? So I'm gonna just take this thing and throw it into a matrix, and we'll call this x0, okay? So x0 is just, it's just this, basically, but in matrix form instead of a vector, okay? And it says, you know, computer, did you figure out that this is the digit 0, all of these numbers here? Right? Okay, well, we're going to just do x0 times the first weight matrix, add our biases to that, throw that in the sigmoid function, take those results, multiply it by our second weight matrix, and throw that into our sigmoid function, okay? Let's take a look at what our y hat vector looks like now. Okay? And this is what our y hat vector looks like. We've got 0.99999, and then everything else is something that's close to 0, right? And so if we look at this, we say, that's pretty good, right? And I mean, obviously, this is not like, this looks terrible. So what we would do is we would take y hat, this thing, and we would just throw it into round. And now we get a vector of 1, 0, 0, 0. And then if we round that and we just, if I say take this and multiply this by the matrix of 0 through 9, this will say, you know, 0 points for that, and then it says, okay, this is our guess. Our guess is 0. Okay? Let's try this again, okay? Let's take a look at another example. J3. Again, our input is just this vector of 784 numbers. What does this digit look like? This digit, to us, it looks like a 4. Let's see if the computer figured that out. All we're going to do is we're going to just use our current weight and bias matrix values. We'll forward feed this through. Let's take a look at y hat. Okay. So y hat, we've got something close to 0, close to 0, close to 0, close to 0, close to 1, and then close to 0, close to 0, close to 0, close to 0. That's exactly what we want, okay? And if we say, all right, well, let's round that off, and then that looks correct, and then we'll multiply that, and our guess, indeed, is a 4, okay? And we can just keep trying this out, and we can see, you know, how about this one, right? What did it guess? It guesses a 2, okay? So I don't know about you, I thought that was kind of cool, all right? All we did was just, this isn't, you know, what this thing means, it's hard to understand, but all we did was we just did some matrix multiplication in a loop, and now we have a way to kind of guess things, all right? And so we can kind of see how good this is, right? So we'll go to our test data cases, and let's just see how well this performed. So I'm going to take kind of the first 1,000 rows of our test data, and then I'll just kind of feed this through, and now I have a whole bunch of guesses, okay? And what we're seeing is we see, wait, this is, you're guessing 16? That's obviously not correct. And so this is kind of our results. And what we see is that when it was 0, we guessed 0 83 times. When it was a 1, we guessed 1 121 times. When it was a 2, we guessed 90. We guessed 2 90 times, okay? And sometimes we get some wrong things, and sometimes it looks like we're guessing 10, 11, 13, or 16. What is going on there? What's going on in these cases is that in our y hat vector, because all we said was a good, you want it to match something that looks like a bunch of zeros and 1, 1. Here, all we did, what could happen is that one of our y hat vectors has a bunch of zeros, but then it has a value close to 1 for 7 and a close to 1 for 9, okay? And in those cases, when you round it off, okay, everything gets rounded to a 0 except the 7 gets rounded to a 1 and the 9 gets rounded to a 1. And so you say, what's the guess? Yeah. The way we're translating from guesses to kind of our y hats to guesses would add those together and say we're guessing a 16. Let's see what, I'm just curious what the test case for that thing is. So I think it was 1,000. So we'll try test. Okay, so here it couldn't figure out what this was. So here it's guessing 16. Let's look at our y hat. For our y hat, it has, a 7 has a value of 0.7 and 9 has a value of 0.66, okay? So when you round this off, when you round off your y hat, it's not sure if it's a 7 or a 9. Which is like kind of forgivable for this handwriting, right? Like, and this is just like, because if you write your 7s like this or something, like, I don't know, whatever. Who writes their 9 like that? Or anyway, great job, person. You stumped our neural network. And this is just like the most simple neural network. All we have is 30 nodes in the middle. Okay, we have a question.
So instead of modifying the gas vector by 0 have you tried choose the
max? Yeah, you could do that. And then you'll only get, huh?
Does it work better in this case?
It might. I could have coded that up, but I just thought, you know what, we'll round it off. I was just kind of lazy, and I said, let's round this off to 0s and 1s and go here. All right. Okay, we're going to run out of time. I wanted to talk a little bit about the midterm exam. That's going to be Wednesday of next week. And I've been hemming and hawing about this decision because I hate to be that teacher that does something like this, but just for the day of the midterm, I think I'm going to have assigned seating, okay? And I will give you kind of a seating chart maybe the hour before the midterm, and you can see where you're going to sit. So we won't be wasting too much time at the beginning of class trying to figure out where we're supposed to sit. I know I hate to do that, but things happened in last quarter, and it was like, because people were sitting next to each other that knew each other, something suspicious happened, and I was trying to think what's a fair thing that doesn't require like Anyway, so I will send out a seating chart like the hour before the midterm. Take a look at it so you'll know exactly when the midterm begins, where you're going to sit down in class, and then we'll go from there. Okay, and we'll do that. I will this weekend. I'll post kind of some information about what you should study for the midterm. There will be you'll need a ruler to do some gradient descent manually, some manual iterations of that. But yeah, I'll post some information about it on CCLE. Okay. All right. That's that. Have a great weekend. We'll see you guys on Monday.